What is an anomer? We have seen several aspects containing to carbohydrates, and this one is may not be clearly defined in your previous sessions, but it goes for all carbohydrates. Here you can see that we have so far represented the our glucose molecule as a linear molecule. Okay, it is not at all cyclic, but here it is mentioned that it is going to take up the cyclic structure. By linear structure, we would mean that we will have some long chain compounds. Okay, but cyclic structure we have seen it takes up the shape of a cyclohexane structures. The conversion is occurring because of the ability of the aldehydes and ketones to react with alcohols and is an aspect of the stereochemistry as well. So now we have clearly seen what stereochemistry deals with. So it is connected with the bond length, bond angles, stability, and the structural presentation. So if you have an aldehyde, let us just take this as some CH3. Okay, if you have an acetaldehyde, if it reacts with an alcohol, you can see that you will get an hemiacetal. Okay, so I already have told you, if you have any carbon atom that has a OH and a OR dash, and an aldehyde's reaction with alcohol, then you are going to get an alcohol, which we have called it as a hemiacetal. Okay, here this one is an example for ketone. So this is aldehyde and this is ketone. So ketone is also reacting with alcohol to give the same type of compounds with the OR dash. Now it says you might wonder why the aldehyde reacts with OH groups on the fifth carbon rather than the OH of the second carbon atom next to it. That means, there is a reactivity preference. Reactivity preference. What is the reactivity preference? It is that the aldehyde reacts with OH group on the fifth carbon atom. Okay, fifth carbon atom. Not the OH group on the second carbon atom next to it. Okay, how? See, for example, it reacts with this carbon atom. Okay, and not the second carbon atom. So if you bring an aldehyde, what happens there? That means, this uh, carbon, which is linear, okay, is actually taking up all the 109 degrees 28 minutes. So here this will also take this 109 degrees 28 minutes. So each carbon atom, it doesn't go linear like this, it bends like this, and again it bends like this, and again it bends like this. So this is the angle that I have mentioned here as a 109 degrees and 28 minutes. So because of this bending, the fifth carbon atom is brought closer to the aldehydic keto group, that is aldehydic group, that C double bond H4. So this is, we have already seen this is known as the Fischer projection. The Fischer projection actually bends like this because of the steric factors. So it gets a three-dimensional representation shown above, and then it is getting condensed with the removal of hydrogen or same any other simple reactions to give a cyclic monosaccharides. Okay. So this picture shows the cyclization of D-glucose. Cyclization of D-glucose. And it starts with the Fischer projection, and then the first carbon atom reacting with the fifth carbon atom. So what it means to say, this first carbon atom doesn't react with this, it doesn't react with this, it doesn't react with this, and it reacts only with this. Okay, so you have three options there: second carbon atom reactivity, third carbon atom, fourth carbon atom, with which it doesn't react. but you have a fifth carbon atom with which it reacts. So the reaction in the first part we saw is that of aldehyde, right? This is an aldehyde group. This is an aldehyde group. Aldehyde group. And this is, you have this as the alcoholic group. So we started with slide telling this thing that an aldehyde group reacts with alcoholic group, right? So we just said that one doesn't react with 2, one doesn't react with 3, one doesn't react with 4, but it reacts with 5. The reason is the stereo bending of D-glucose. So because of that, it bends like this. Okay. Now the question is, why does it bend like this, and what do you call these bendings? When you have a straight chain molecules, the carbonyl oxygen, the carbonyl oxygen atom may either be up or down, giving rise to two stereoisomers as shown in the figure below. Two stereoisomers. Okay, one in which C double bond O may be on top, the other one in which C double bond O may be at the bottom. That is either up and down. I am writing it here as shown in the bigger floor. The structure shown on the left side of the figure 24.3.2, this one, is in the OH group. You can see this. The structure shown on the left side of the figure, this figure is the OH group, and the first carbon atom is projected downwards. Here it is, which is called as the alpha form. The structure on the right side with the OH group on the top. With the OH group on the top, where is it? Here. So this is low or down, and this is up. Right? The structures on the right side with the OH group on the first carbon atom pointed upward. It's called as the beta form. This one. The two stereoisomers of cyclic monosaccharide are known as isomers. Now, this one and this one, in which one you have as down, right? As down and up, are actually called as the anomers. And the carbon to which they are attached are called as the anomeric carbon. Okay, so I am going to read that what its fallout is. So here it is. It is possible to obtain a sample of crystalline glucose in which all the molecules have all molecules are having a beta structure. Beta structure means it is the upward form. Beta. This is alpha and this is beta. In beta you have upward form, and the alpha form melts at 146 degree and has a specific rotation of plus 112. This is 12 degree and this is 112 degree rotation, while the beta form melts at 150 degree C and has a specific rotation of plus 18.7. This is the rotation, plane polarized light rotation. So I think I told you about this, plus 112 degree plus 18.7. If you mix these two solutions, you will get a resultant of something like 54 degree, and you will get a mesoform. I think I have already told you, one form right rotatory cancels the left rotatory form of the glucose. However, a mixture soon produces produces an isomer with a straight chain in the dynamic equilibrium, and you can start with a pure crystalline sample of glucose consisting instantly isomer. But as soon as the molecule dissolve in water, they open to form the carbonyl group and reclose to either form alpha or beta. So they open to form a carbonyl group, and then again reclose, open and reclose. So these things are very common in the chemistry point of view. We also call as the ring opening and exchange of the protons, and you have a subsequent subject connected to this called as the molecular rearrangements. So here it goes that it at equilibrium the expression consists of about 36% of alpha D glucose, 36% of alpha D glucose, and 64% of the beta D glucose. So remember, beta means up. This one is about 64%, and this one is about 36%. Okay, and less than 0.0% the open chain. So very less. So it is somewhat almost equivalent, not at all present. 0.02 is very less. And the observed rotation is about 52.7. Well, this is what I mentioned here. It should be 52.7. So it is something like an average. 112 plus mixes it plus 118 gives rise to final thing as 52.7. Okay. And the structure below that is given is again the same thing. Here you have this is a that is a hexose type of structure where you have 6 hydrogen carbon atoms, and here it is a pentose type of glucose where you have 5 glucose atoms. Again the same thing is there. You have OH down here and OH up here. Therefore this carbon atom and this carbon atom both are having anomeric properties. Therefore they are called as the anomeric carbon. And this is anomer of this. This is an anomer of this. Okay, now you understood. So the simplified form is you have one hydroxyl group upwards, it will you call it as a beta, and in the next thing you have the hydroxyl group downwards and you call it as the alpha. Even though a small percentage of the molecule are in the open chain aldehyde form, I think we just saw this as 0.02%, right? It should be negligible. The solution, in spite of that, has exhibit characteristic reactions. Okay, characteristic reactions of aldehyde. As the small amount of free aldehyde is used up in the reaction, there is a shift in the equilibrium to yield more aldehyde. Thus, all the molecules may eventually react, and even though they are little, that what is mentioned is even though there is no free aldehyde present, even though it is having only 0.02%, 0.02%, it reacts. Okay, so you have very less amount of open chain. If there is no open chain, there will be no reaction. But even 0.002% is there, it reacts. So that is what is means. So the cyclic forms of sugars are depicted using convention first by Haworth formula, and then as planar hexagons, which we call it as the 3D, and then the side facing upward and downwards. I told you upward it is alpha structure, upward it is beta structure, downward it is an alpha structure, alpha form, and the structure is simplified to show how its reactivity is there. So again, I'm just going to mention this cyclic structure of this, right? So here, this is what we mentioned. There is an aldehyde group here because we have alpha carbon atom. So there are so many OH here, like this, like this, like this, and like this, and here you will have CS2OH. So this free OH, this free carboxyl group, it doesn't react with this, doesn't react with this, doesn't react with this, but reacts with this because by bending, it brings by stereo bending, it brings this molecule comes closer to this, and you get a condensation by removal of water, and you get a cyclic form. Okay, so this is a open chain form. Open chain form starts bending. Open chain starts bending and then makes a cyclic form by the removal of this water molecule. Okay. So in this process, if you can have COH at the top, COH at the bottom. So this we call it as the beta, and this we call it as the alpha. Okay, and both of these give rise to anomers. There are two anomers. So in fact, these are some kind of the isomers. So I think we have learned a new thing from this slide, from this presentation. And the summary is monosaccharides that contain 5 or more carbon atoms from cyclic structure in aqueous solution. Two cyclic stereoisomers can form each straight chain cyclic stereoisomers. It is already cyclic and can form straight chain monosaccharides. Cyclic, it will be like this. Okay, for a brief amount of time it opens up like this. Okay, and then these are known as, when it opens up you will have reactivity. Open agalana reaction irukadu, so it will have reactivity. These are known as the anomers, because in which you, when it opens up, one in which you have OH at the bottom and the other in which you have OH at the top in aqueous solution. So the equilibrium mixture of these two anomers and the straight chain structure of this process is known as the mutarotation. We have already seen the mutarotation of the glucose, and I'm stopping with this. We have learned a concept of the anomeric forms of the carbon atoms. That is, the cyclic form opens up and it gives rise to two types of structures because of the orientation of the OH group at the top. If you have OH orientation at the top, it will be beta, and if you have orientation at the bottom, it will be an alpha form. And this alpha form doesn't react with adjacent carbon atom but reacts with the fifth carbon atom, because the molecule, the carbon atom, the chain again bends it, and that brings it to the first, that is the aldehyde carbon atom. Condensation takes place, and when you have two forms, you call it as alpha form and the beta form. They have got a specific melting properties as well as specific rotation, and then reactivity pattern also varies there. Thank you for joining me. See you around.